Yes. So, Sebastian, your talk is the space of one-dimensional dynamical systems. Happy birthday. Where is Sebastian? You can start.
You have to unmute yourself, Sebastian.
So before I start my talk, I want to first say something about Lorenzo. I mean, it's quite pleasure to give this talk. I mean, one of the main things I've always find about Lorenzo is the amazing energy and you know, fun that is sort of when he's around. So, and I think this is really something I want to kind of celebrate in mathematics, that we, you know, this energy and fun. So I'm going to just delete this because otherwise I'm hiding. Is it possible to see this? I think Felix, probably your camera, can you see the screen?
Yes.
Okay, good. So the problem I'm looking at is interval maps. Well, I've done that before, as you all know. So I'm looking at interval maps or circle maps, and I want to really look at the entire space of such objects. So that I knew with this space of real analytic interval maps, and I have a finite number of critical points, and they all have a degree, which I denote like this. And as usual, I say that F and G are topological conjugate if there's a homeomorphism that conjugates the two. And now the aim of this project is really to describe this, topological conjugacy class. And I'll sort of make that more clear in the next slide, what sort of question I'm really looking for to answer. Now, of course, a sort of a very primitive, to my mind, way of answering this question is, well, a very useful way also, but you know, not the full answer is that you say, well, hyperbolic maps are dense. Hyperbolic maps, you know, everybody knows what it is, but I will sort of come back to that later also. But this doesn't really answer the following question. You know, you have this full space. How is this space partitioned in conjugacy classes? And that's the kind of question I really want to focus on. And well, I've given a similar talk to this before, and you know, the main difference is what is under the hood, and I'm not going to be able to discuss that. But anyway, please bear me, and I will try to sort of talk a bit more from a philosophical point of view, because the kind of question I want to say is, well, suppose you have this full space, and now you look at the conjugate class of a particular interval map. And for simplicity, let's sort of assume that the map has no parabolic periodic points. That assumption is not really necessary, but it simplifies some statements a bit. And
what is parabolic?
Parabolic means that you have no periodic points which have a neutral, you know, multiplier equal to 1 or -1 in this case. So it's not globally parabolic. So this really talks about periodic points and the spectrum of those of the multipliers.
Okay, thanks.
And so the first theorem says, well, actually, conjugacy classes are connected. And well, this is in some sense quite a remarkable result that you know, you look at this full space of maps, you know, you have this huge space of maps, and now you take two maps which are conjugate. Well, in fact, the claim is if you have such a map F and another map G, then there's actually an arc connecting the two. So you can find a real analytic family of maps that connect the two. And of course, in general, you can't expect this in higher dimensional systems. But for example—
It's more than connected, it's path connected.
Path connected, yeah. In this case, it's path connected. It's even better than connected. And the kind of question you can ask is, for example, suppose you take higher dimensional systems. For example, more small diffeomorphisms on two-dimensional manifolds. My sense is that the answer to this question is no, but is it possible that in this case also the conjugacy classes are connected. So can you always partition the space in connected subspaces? So that's the kind of the first type of result, which is we managed to achieve. And the second type of result is actually even better, to say, well, suppose you have this conjugacy class, does it have some additional properties? And as I mentioned, I don't want parabolic periodic points for this statement, at least for the moment, and also no attractors. I mean, attractors I'll come back to in a moment, but well, then in fact, this space is still a real analytic manifold. This whole conjugacy class is a real analytic manifold. And in fact, you know exactly what the dimension, or rather the codimension of this infinite dimensional space is namely equal to the number of critical points that you have. Now, I mentioned already these assumptions about parabolic points and periodic attractors are not really necessary. They're only necessary for the second part. Otherwise, you have to count the dimensions slightly more carefully. For example, if you have lots of periodic attractors, then of course you need to sort of look a little bit, what that means, and the attractors can be in one and another. So the situation is slightly more complicated in this case, if you have periodic attractors. But in fact, even then you can say something, but then you might actually prefer to look at hybrid conjugacy, which means that the multipliers are assumed of two conjugate maps are even assumed to be the same. So then you redefine the space of conjugacy class by hybrid conjugate, which essentially means that they're conjugate, and moreover, the multipliers of the periodic attractors are the same. The corresponding periodic attractors are the same. And in fact, also you need some additional information about basins in periodic attractors. But this is, you can make a very precise statement, but that's probably not really so useful for this talk. So that's the second kind of result. And again, you can ask, is there any sort of similar property that you might have in higher dimensional systems? Of course, if you have very general systems, you don't really expect that. But here, in fact, there's, such a map may be very far from hyperbolic. So you also can't really expect that much. But nevertheless, these properties hold. Now, the third statement is again about hyperbolicity, but now about within families. So let's take a family, and that depends on the new parameters. And new is the number of critical points that we discussed. We fixed the number of critical points for these maps. And so that's the dimension of the parameter space. And then we're going to assume that F lambda is a family of S-like maps. And what that means is that, well, if you want, you can assume that the maps have negative Schwarzian, or maybe that every periodic attractor has a critical point in its basin. So what you do not want is something like this, something where you have lots of periodic attractors that are kind of here, and then maybe here's a critical point. And all these periodic attractors have nothing to do, well, not directly something to do with this critical point. And so that's what you want to rule out. And I'll explain in a moment why you want to rule that out. So that's the first assumption. And the second assumption is that you are going to assume that the family is kind of full. Well, what this kind of rules out is that you don't take constant families. So you want all the kind of dynamics that's nearby already to be contained in this family. Now, then the property that we assert is that the set of parameters for which this map is hyperbolic is actually open and dense. So that's actually stronger than the statement that in the full space of one-dimensional maps, these maps are the hyperbolic maps are dense. Here, it's really, if you look at families of maps of the appropriate, where the dimension of the parameter space is sufficient, then it's going to be open and dense. And well, somebody asked already, essentially about what do I mean by hyperbolic? Well, in the case of hyperbolic in general, of course, this means you have this decomposition of it, of the non-bounding set in particular pieces with, this splitting and so on. In this case, it's much easier because in one-dimensional case, it's that all critical points are in the basin of a hyperbolic periodic attractor. And so yeah, this is the kind of thing that you want to so that's of course not always the case. This is of the property, but if you have this property, then in fact you have the usual standard definition of hyperbolicity. So then you have the non-bounding set splits in a attracting part and an expanding part. And in fact, in this case also, the non-bounding set will be have measure 0, and almost all points will be attracted to periodic attractors. And in this case, the attractors are sort of simple. And well, why do you want to assume this this S-like assumption? Well, because if you have loads of periodic attractors, like in this picture here, so you have here several periodic attractors, well, then in fact you need more parameters, because you could sort of easily imagine that you have a family, and well, let me kind of draw that here, which has several tangencies. Well, this is meant to be a tangency, and here's a tangency, another tangency. Oops, this is meant to be not a critical point, but anyway, that's the picture I have in mind. And of course, if you have so many periodic, parabolic points, you need more parameters to kind of unfold this and make this hyperbolic. So the statement, I believe, is still true, but you would need this this space to be more, this space n to be larger, and so you can make a statement like that also. But anyway, that's the reason for that assumption. And the assumption that you have that this dimension, is an open subset, is that because if you take a family of a lower dimension, you can create sort of some persistency in it. You can sort of make sure that, for example, one critical point maps to another critical point throughout the family, or some other degeneracy holds. And then you will not be able to create sort of hyperbolic maps within this family. So that's the other statement. And for example, this actually is.
Sorry, Sebastian. What is locally full in your definition?
Well, one way of stating it is that. Well, let me answer it in a rather sort of intuitive way. What I mean by full would be that you have all the itineraries that you could, all the needing invariants that you could possibly expect, you have in this family. And locally full means essentially that all the nearby needing invariants exist in this family. And this is something that there is sort of very easy ways of saying that. For example, that you have certain return boxes, and then the families really go from one side to the other. So it's a topological property. And for example, a unimodal family which is full is, for example, one that goes from here to there. One parameter family like this. But in a multi-parameter family, bimodal family, you have also a similar property. For example, you have maps. Oops, you have a map like this in it. Oops, what am I drawing here? This is a degree 4 map, and well, all the possibilities where all the critical points touch the appropriate boundaries. For example, this map is inside, so you can make an easy statement of this form. Does that answer your question, Lorenzo?
Yes. Yes. Thank you.
So the corollary of this question is, for example, of this theorem is that if you take this family of real trigonometric polynomials, and well, it's written down here, that in fact hyperbolicity is dense in this space. And that result makes me very, very happy. In fact, it's also sad because Wellington often asked me and said, well, this is something going to be impossible to prove. And well, yeah, so it makes me really happy that, we are able to prove this. And the reason he asked that is because we had Lasse Rempe and myself had another result, and that assumed that in such a family all the critical points are real. Well, of course, this map will have critical points, but they may or may not be real. And in the previous result, we needed to assume that the maps are real. And also we needed to assume that the maps are kind of globally defined. And well, we don't need to use that anymore. And the reason for locally defined was that we use some kind of straightening lemma, which means that you kind of take a map, sort of make it local by some kind of complex box mapping, which I'll discuss in a few slides, and then kind of glue it with infinity in a kind of artificial way. And that's not possible in maps of this type. So for polynomials, you could do that, but for transcendental maps like this one, that would not be possible. But our technology is quite different. And now I will kind of discuss that a little bit. So the next result, well, this is actually not our result, although Arthur did not give a proof of this in his paper, but of course, it's he at some point also explained on the blackboard, how he would do that, and essentially, if you had taken a map, effective map which is parabolic, and it's unicritical. So this is a unicritical map. And this has some kind of, this is the unicritical map. And then you take some kind of iterate and maybe, something which has a parabolic fixed point. Well, this is a very simple one, but let's say something like this. Then you can construct it in such a way, not always, but you can construct it in this way that this map F can be approximated by other maps so that the conjugacy classes are more complicated. So here's some map F, and here I'm going to construct some sequence of maps F, and here another map F2, and there's another one F3, and these are meant to accumulate on this F. So you have here this kind of particular map F0, and this accumulate this map F2 and F3, or rather the conjugacy class of this F1, F2, and F3. And so this whole sequence. And again, even within this, there's also some similar statements. Maybe I should draw, well, I can draw this in a different color. Let me first, so there would be some other thing, and I hope I can draw this without making a mess of it. So you can see here that there is sort of a similar kind of sequence inside here. There's a whole sequence of here and in here and in here and so on. And so you can make a construction where there is no lamination of this conjugacy class.
Sebastian.
Yeah.
So these are drawings not of the maps, but of their conjugacy classes. Is that it?
That's right. Yes, absolutely right. So strictly speaking, thank you for asking. This should be really this conjugacy class key.
See that? Good girl. It's going to get busy. Come on. It's going to get busy. You can have those later. Have that later, okay? No. Come on.
So I can't hear this.
Sheldon, turn off your microphone.
So I think and now what we hopefully that's work in progress is that in fact, if you take analytic maps and now also impose the additional property that the Schwarzian derivative is negative, and this is our unimodal maps. And you fix again the degree of the critical points. Then these hybrid classes laminate the neighborhood of each mapping. So what does that really mean? That means that in this case, the picture is not like the previous one. It's kind of really, as you kind of hope, that the conjugacy classes are, essentially following infinite dimensional leaves. And, this is the T, well, like the question just now, this is T of F1 and T of F2. And each leaf kind of nearby forms some kind of real analytic manifold. And the property that you then have on top of that is that if you take, you can find a transversal family, which is the one I draw in purple. And this transversal family will have the property that each leaf will be intersected at precisely 1 point. And
what is the difference between this and the previous negative result by Arthur?
No, this is the opposite, because what happens here is that, for example,
No, I understand, but what is the difference in hypothesis? I suppose the conclusion
okay,
is so different.
thank you for asking. Yes, so here the maps are not don't have negative Schwarzian, and that's sort of somewhat surprising. And in fact, Arthur, he still does not believe the result, and so we're kind of writing it, and but we're actually convinced that the result is correct, but it's a subtle result. And because negative Schwarzian a priori, it's not quite clear what this has to do with these, conjugacy classes. So what the claim is that if you want to construct examples like this, then you're going to fail if you also impose the negative Schwarzian assumption. So a consequence of this result would be, and again, that's sort of we're writing it at the moment, is that if you take one parameter family of real analytic maps, which are sufficiently close to, well, and in fact they're unimodal because they're sufficiently close to real quadratic the real quadratic family, then the entropy is monotone. So, for example, if you take this family, this famous family, and you take another family which is close to it, then so far there's no result that tells you that the bifurcation diagram would still look like this. But
what does close mean?
Well, what close means that you can do any kind of topology because it's real analytic. So C0, for example, and C0 means also C.
Okay, I see. Okay.
Yeah. But yeah, that's sort of crucial. But it does mean in both, as a map from Z, T to T to FT, Z. In that sense. So this family should be close to the to this family. So let me sort of talk a little bit about the relationship with previous results. And so there's earlier results, much earlier results by Lubitsch in the context of quadratic-like mappings. Well, in quadratic-like mappings, I guess I will just draw a picture in this thing. These are maps now not of the interval, but of the complex plane. And that means they have some domain U that maps to domain U prime. And U is compactly contained U prime. And this map is quadratic-like in the sense that there is one critical point, but at every other point, there's a degree 2. So it's a branch critical covering map. And, there's still, the extra property is that you assume that you look at the connected locus. So that's a set of points, a set of maps, so that the points that do not escape, you have here always sort of points which maybe I'll draw in black. Let me draw it in black. So you have this set of points which I will kind of draw very kind of roughly. Set of points that do not escape from the domain of definition, U. And well, that's this set of K of F, the Phil-Julia set, it's often called. And now you ask for the set of maps, you consider the set of maps where this set K is connected. And that's called the connected locus. And then you again look at this hybrid class, which is the topological class, plus fixing the multipliers at periodic attractors. Well, and in this case, the map can have only one periodic attractor because, you have this global structure. That means that every attractor will have a critical point in its basin. So what Misha is then able to prove is that in this case, the conjugacy classes are connected and codimension 1, and they laminate in the way we had in the previous result. So that's a beautiful result, but it really imposes a very strong assumption that you have this quadratic-like structure. And that's certainly not satisfied in general. If you take a real analytic map, you will just simply not have that. So that's the first result that goes there. And then let me sort of talk about other results that are kind of, that we build on. Is that is a paper by Avila, Lubitsch, and De Melo. And they prove also connectedness, but in a particular setting, namely, the critical point needs to be quadratic. So, for example, unimodal, but degree 4 is not possible in their case. And non-renormalized, well, they need to have the map to be non-renormalized and unimodal. So we're able to kind of remove all these assumptions. And it turns out that actually is something quite different. You really need a completely different approach to the problem. And I'll explain in a moment also, one difference. And the manifold structure was proved previously also by them, but only in the unimodal case. And again, be able to remove this. And the density of hyperplasticity in families, that was proved by Kozlowski, but again, in the particular case of quadratic unimodal maps. And the result about this lamination was proved by the 3 authors away from parabolic maps. So they were able to prove something like this. And our hope is that eventually our techniques even extend to C3 maps. Now that's some way off, but currently we need that you have an holomorphic extension of a real analytic map. But in fact, some of our results already work if you have an asymptotically holomorphic extension. And then this asymptotically holomorphic extension is enough to really use enough of the, the complex analytic machinery that makes things kind of a bit easier. So let me explain roughly, what our approach is. Well, the tools, which I will try to elaborate on in the rest of the talk, so they come from 3 different parts. And the first one is actually, to my mind, quite an interesting one, because what we show is that you have, if you take a real analytic map, you have some kind of Markov structure, but it's sort of a partial Markov structure. And I'll explain a little bit more about that. The second ingredient is quasi-symmetric rigidity, and I'll discuss some of that. And also, of course, the measurable Riemann mapping theorem. And I'll explain that, because in this audience, that might not be a standard tool. And one of the things is we are able to do this if you have several critical points, and there is really sort of a difference there, because the thing is sort of more convoluted, but perhaps even more importantly, we do not assume that you have big geometry, which is actually one of the main things that makes the previous results work. And that's why they need to assume quadratic critical points, because in the quadratic critical point, there's some kind of magic that tells you that in this case, you automatically get this big geometry. And that's actually not true, even in unimodal maps with degree 4, for example, or bimodal maps with quadratic critical points do not have that property. So this is really
Can you say a little bit more what big geometry is?
Well, essentially, it means something like the following, that you have some puzzle pieces. And what I really mean by this is that you have some kind of domains in the, and you look at first return domains. So you have a first return map to some kind of set P. And now you look at the first return map to P. And basically what you want is that if this set P is small, so if N is sort of deep in some kind of inductive process, that the next one, which I'm going to draw here, or in fact all of them, will be super small compared to the previous one. So what this kind of rules out is that, by chance, the next level is going to be roughly of the same diameter as the previous one. So there could be, in general, there will definitely be the possibility that some puzzle piece maps to a piece that's kind of roughly of the same size. And this big geometry essentially even requires something often more, not only that this is P plus N, not only that these puzzle pieces are small, but actually that the diameters shrink to, the ratio of the diameters shrink to 0, not just shrink to 0, but exponentially fast. So this is a consequence of this quadratic critical point assumption.
And
But
this
that's
isn't true for x to the 4 or something, for
No.
fourth power.
If you take x4 plus a constant, that's not going to be true in general. There are many examples like where this turns out to be not the case. So yeah, so I'm going to talk about these tools a little bit. And of course, if you take a complex macro structure, in fact, in all of dynamics, this is kind of a crucial way of looking at it. And then sometimes for ergodic properties, you can sort of go away from it. But if you look at really more topological properties, then I think some kind of macro structure is often kind of fundamental. And one thing is this complex box mapping idea. And that's really what I'm going to drawing here. You have these kind of sets, and which I draw here. And these are the ranges. So these are the ranges. And then if you take the first return map to the ranges, some of the domains will be compactly contained in the ranges. This will be compactly contained in the ranges, so this domain. But some of the domains will actually be also a component of the range. So this will be, for example, both a component of the range and of the domain. But this domain maps here, and then maps here, and oh no, I drew the arrow wrong. It's this way around, and so on. So this is kind of schematically what this means, and this is very useful to have. And if you have globally defined maps, sort of like polynomial maps, then often you can construct these quite soft tools. But often you need not just the existence of such things, but also some additional, bounds, and that's often going to be the case. But anyway, the point is that this often only defines something on a necklace neighborhood of I. And what do I mean by a necklace neighborhood? You have your interval, and now you have the complex plane which is kind of surrounding it, and then you have this kind of neighborhood, and this kind of neighborhood is kind of like this. So it's kind of the neighborhood of the set that you're going to use. Does not fill it's not a full neighborhood of your interval, but it's something like a necklace. So the very, very thin pieces like here, where the diameter shrinks to 0. And so this necklace neighborhood is not really a full neighborhood of the interval, and that will cause troubles. Now, if you also assume then that you have this big geometry between successive levels of the puzzle pieces, so this is sort of maybe a puzzle piece, and then maybe there's a critical point inside, and then in fact you can still do something, and then you can still obtain some kind of QC neighborhood in the neighborhood of the interval, and that works well. But that requires this big geometry. And then, of course, if you take that and with the measurable Riemann mapping theorem, you can connect two maps, and I'll come back to that later. So let me not discuss this at this moment. This comes in a later slide more in detail. So that's sort of roughly their approach, and that doesn't really work so well for us. So what what we propose is to do something a bit different. And I'm actually quite, I find it quite cool. So let's think now that, so suppose that this map extends to a polynomial map or polynomial-like map like this. And well, let's actually let me actually write here C to C. That's maybe easier to think of this as a map from C to C. And so that, if you're on the outside the interval, but it's still in the real line that you go off to infinity. Well, then in fact, this, as Julia said that I discussed, or the filled Julia set, it doesn't really matter, is equal to this set here. This set is really the pre-images of your interval, and you take all the union of these things and then take the closure. And this is sort of when you have a globally defined map. And now what to do if you have a real analytic map? So the idea is that I want to start with a real analytic map and still introduce some geometry, or well, in the first instance, topology. And so I'm going to kind of introduce some kind of sets, kx, and this is of a pruned set. So what I'm going to do is I'm going to cut the set here, and I'm going to, in the next slide, so draw this more. I'm going to take my gardening scissors and, you know, this Christmas tree, I'm going to very carefully prune. And let me kind of explain that more in this picture here. So I take a neighborhood of the critical values. So here there's one critical value, and I take a neighborhood of it. So here's a kind of neighborhood, and maybe it is just an interval. So here maybe this interval. And now what I'm going to do is I'm going to define the analog of this, taking pre-images of the whole interval, but no, I'm not taking the whole interval, but I'm going to take the pre-images, because let's think about this. You know, how is the Julius set here created? And well, I mean, if you took the whole Julius set, which is kind of a bit of it is drawn here, then in fact, you know, this point here has, well, let me draw the real graph of it, which gives you sort of a flavor.
So why there are two equal pictures there, Sebastian? Sorry.
No, they're not equal, and I'm going to explain why they're not equal. Because, you know, let me sort of go ahead a bit, because probably you can see there is a difference here. It's see the difference pictures like in the newspaper. You see, you know, you have 12 differences, and you know, this is the kind of thing. So what I'm saying is, if you take a point here, which is sort of where the value is, you know, above the minimum, then you have two real pre-images. If I take a value which is below the minimum, there are no real pre-images. So what's the pre-image of this bit here? That's sort of these, you know, this bit here, which is stretching all the way here, right? So this is actually, you know, this bit is created by a pre-image, which if you were only looking on the real line, you wouldn't notice. And so this is of the, you know, if I took a pre-image below the value of the map, then the pre-images will be, well, in this purely quadratic map would be purely on the imaginary line. And so what I'm doing is I'm taking an interval around this thing, and I can take a bigger or a smaller interval, and taking a smaller interval means that I get more cuts. Because you can see I take here a big interval here, for example, something like this interval up to here. And then I can still get here, but here I have pruned it. You see here, there's a prune here, there's a prune there. And maybe I hope you can see it on your screen, but there's a lot of prunes here. And, you know, there's prunes here. This is, if I was having a normal Julius set, this would be a connected set. But I have pruned already. And depending on the size of this interval here, I prune it, you know, I prune it more. And you can see here that if I take a smaller interval here on the right, rather than the bigger interval, which on the right, which in fact you can't see so well here, your interval, your object kind of shrinks to your interval. It sort of comes closer and closer to your dynamic interval I. So that's the object here. I want to have defined some kind of object, which is going to be my set Kn, which is kind of that union, and the closure of that. And that's going to be some kind of really interesting topological object. And that's the reason I want to prune it is because, remember, in fact, this picture is fake. I mean, this picture is fake because, I mean, maybe the map is only defined. I mean, my real analytic map has only a complex analytic extension on this small piece. So all of this doesn't even make sense. I couldn't really, you know, even make this meaningful. So what I claim is that if I take these intervals J sufficiently small, then I can make sure that this whole construction remains meaningful. And I get a set Kx, which has a number of properties. First of all, it's locally connected. Secondly, if you have suppose the map has only repelling periodic points, the real analytic map has only repelling periodic points, then all the periodic points on this in this set here, there will be, you know, many non-real ones for this map. You know, you have still a map from F from Kx to Kx. And in fact, you have it on some neighborhood of this set Kx. All these points will be actually repelling also. And in fact, if you have an attractor, then, and it's hyperbolic, then the periodic attractor will also be hyperbolic, and in fact will be contained in the real, on the interval, in the real line. So in a sense, we have kind of defined this associated to your dynamical system, some geometric object Kx.
So, okay, so sorry, but this is something that's playing the role maybe of the Julia set in the, so these maps are not polynomial-like.
They're
So
not
this,
what like?
They're not polynomial-like.
No, no, absolutely not. In fact, in some sense,
that's why I'm making all this effort to construct a Julia set-like thing. Is that it? Or?
No, but the point is, I want to construct something that is almost as good as polynomial-like. Okay. So I don't have a polynomial-like mapping, but I would love to have one. And so what I'm going to do is to obtain, to have this kind of, you know, somewhat involved construction and then obtain a polynomial-like mapping. If you assume it from the beginning, then of course you don't have to do anything. Right. But here we kind of construct it. And what I'm outlining here is the technique for doing that. And so we have this locally connected set. And now we can take the complement of this compact set and take this Riemann mapping, you know, this Riemann mapping between these two spaces. And well, this map actually extends because the Kx is locally connected to the boundary of D. And in fact, there will still be some inverse of this map, but it's a multivalued map. So, I mean, just to kind of explain, you know, you have here different approaches to this point here. You have here 4 points, 4 ways of going to this, you know, this point, this critical point. And all of those points will actually correspond to the same point in Kx. All these limits will compare. But of course, if you know, the Riemann mapping will sort of essentially say, well, you know, I have this way of going to this way, and this way. So these 4 points will correspond, these rays that I've drawn here will correspond to curves going there. And they, in Kx, they all collapse to 1 point. And now the point is that I can sort of define this, you know, this object here, which is kind of looking at my object, my map here, but now from the complex point of view, taking this very small, suitable neighborhood of the, you know, dynamical interval I. And then this map G that I have here extends to the boundary of the, you know, the disk. As an analytic map, except at some points where you have jump points. And in fact, here, I've drawn here this map G. Here's the circle. You know, this is meant to be the circle. And this is, you know, if you were to have a polynomial-like mapping, then this map would be actually a degree 2 mapping of the circle, just a standard continuous expanding map of the circle. Here, it's not like that. So here, it's not that because you have discontinuities, you know, like that. And they correspond to, you know, going from the left side or the right side and the left side to the right side of these different critical points. So that's, you know, one reason. And also they don't need to be expanding because the map may have periodic attractors. But suppose you then also...
So this picture on the left has 3 connected components. You're not using them all, right? You're only using the middle
That's
one.
Right. That's right. Actually, that's good you noticed that. It's very sharp you noticed that. So what I do is I delete this part and I delete this part. So that's absolutely right. So what I only use is the bit that's not drawn in blue. So I use this connected component that's attached to the real line. And I've drawn this here just, you know, if I had more time, I would sort of go deeper into that. But you're absolutely right. So, and now the point is that this allows me actually, you know, if I do some more stuff, actually to affect, use some kind of adaptive metric here, which makes this map actually become expanding as a map of the circle. But outside, you know, if I draw here, here's these 2 intervals, you know, around this, no, we had in the previous slide, we had this, actually, let me draw it like this. So you have these sort of jump points and these critical points, here, and these critical points here, they correspond, I take a small neighborhood to correspond to these intervals here, and I'm going to ignore the map there because the analyticity properties at this point are really subtle. So I want to kind of avoid it, and I don't need them. But then, in fact, the map, I get two pieces, and this is my almost polynomial-like mapping here, which is, I think it was Andre who was asking these questions. So here they have this piece and then this piece, and they all map to the bit which is in dark gray. So this bit maps here, and this bit maps kind of all the way here. And if I then go back to the original mapping F, this is my mapping F, which is the one that I'm really interested in. I get something which is almost like a polynomial-like mapping, but it's not really, because I don't have that U. Well, I have a map from U to U prime, but U is not compactly contained in U prime, and so that's not true. In fact, you can see here U is sort of, and U prime have a common boundary there. And also you see there's a bit of U sticking out of U prime. So there is sort of kind of differences, crucial differences. But with this, we are able to construct what, is prune polynomial-like mapping. And, roughly speaking, the properties are described in this theorem. So you have a map from between two neighborhoods, U and U prime. And these are neighborhoods of your interval I. And you have some finite union of curves. And the map sends U to U prime. And the bound of U to U prime uniting this finite number of curves. You see here this curve of U, this bit actually will map to here. And so you see that U prime has no boundary there. That's why I have to have this gamma. So gamma is kind of, a piece of gamma is sitting there. And this gamma, it's sort of like invariant curves. Well, invariant curves, these are pre-images of invariant curves rather. They're sort of, this curve maps eventually maybe to this one, and this one maps over itself to this one. So this is sort of what people call external ray. And so that's sort of the idea that but those come from the local construction. They are not coming from some kind of Böttcher coordinates or something, because we don't have that here. And then the other property that we want is that this difference is a quasi-disk. So this means that we essentially have something. And
so this picture that this computer picture is a computer picture. It's not made with an actual example. Yes, this was a computer picture where we did some things by hand, but yes, simply because we had to sort of tell the computer what to do. But this is not like Z squared plus C or something.
Well, you could think of it. You could think of the Z plus Z. You could think of it as this map Z goes to Z squared plus C. But now you tell yourself it's only defined on a very small neighborhood of the real line. And suddenly you cannot use the global properties. Or, for example, it could be actually a genuine real analytical map that has no complex extension beyond the such a neighborhood. And so you want to make sure that...
What I was asking is whether this is a real picture for a map which does not have an extension. Or, I mean, this is just a silly question, sorry.
Well, it could be, yes. I think it's a correct picture. I mean, this picture is really, the precise topological picture. But I mean, of course, yeah, I mean, of course, no, I have not drawn something where you don't have a big extension, because it's kind of, more difficult to work on the computer, particularly for me.
Sorry.
So I'm going to skip this slide because I think that's probably less, that's probably more detailed. So the next ingredient is this property that if you take two maps, then Sullivan had this conjecture that if you take two maps, and in fact this was a much more general kind of question, if you have topological conjugacy, do you have stronger conjugacies? And what we claim here is that you have in fact quasi-symmetric conjugacy, where quasi-symmetry means the quality of the conjugacy, H. And H is, satisfies this kind of inequality. And if you have this property, then in fact it extends to a QC map on the complex plane, but not necessarily as a conjugacy. So this is, so the theorem that Trevor and I, have, and I will make one comment on the next slide. So is the following, that if you have two such maps, and assuming that the conjugacy is a bijection between the set of critical points, and corresponding critical points have the same order. So if the first critical point, the most on the left, has degree 4, then the first one, the other map also is, the leftmost is also of degree 4. And parabolic points map to parabolic points. That I need to assume, because topologically parabolic points and expanding points are kind of the same. You can't see them on the real line, but in the complex, of course, you can see them. So that's why we need to assume that. But then the map F and G are quasi-symmetrically conjugate. And this is actually quite useful. And well, this is actually, a new result, because here we don't need to assume that all critical points are real. And it's a global quasi-symmetric conjugacy, not just on some post-critical set, because sometimes you say, well, you have some map H, which is only defined on the post-critical set, the forward intervals of critical points, and not on the whole interval. But we want it on the whole thing for a reason that will come clear in a moment. And in fact, also a new thing is that the map that we look is that the maps are C3, and this could be one possible application that we might want to develop is a C3 renormalization theory. And one thing that I'm actually at the moment writing up is in this thing we need something about particular nest of puzzle pieces, and this is sort of quite surprising that you could find a sequence of puzzle pieces. Well, actually, let me draw it in a set of puzzle pieces. So this is sort of a nest is of G0. This would be G1, and so on. So the nest is, and they have bounded geometry. And what do I mean bounded geometry? I want to rule out this situation that the set could be like this. So the diameter is much bigger than the inner diameter. I can, for example, I find for Bat's case that I want to rule out, I could perhaps not find a disk around, say, the critical point that is of the same rough diameter as the total diameter of your piece. So that's what I mean by bounded geometry. And also what I want is that if I take such a piece, that the GNs are have the property that if I take the first return map, that these first return components also have this property of bounded geometry. And moreover, are well inside. And well inside, I mean that I have some modulus bound. If I pick one of these pieces and I take the modulus of the difference, that's bounded from below, uniformly bounded from below. So I can't have a big piece close to the boundary. The pieces really need to shrink in a very precise way. And this nest is very closely related to the principal nest. And I'm going to run out of time. So I'm not going to really talk about this so much, but this is somewhat surprising because in fact, in general, if you look at these puzzle pieces, they can be definitely have this shape. This definitely can happen. But we have, we already knew there were different nests, like it's a different story, but enhanced nest may have this property. But for our application for C3 maps, that was not quite enough. And so we have these GIs. And, we kind of make that discussion slightly more, well, much more, precise than what we have. So then, just let me kind of close here what the idea is, then, to prove that you have this connectedness. Well, you have this quasi-conformal mapping, which is a conjugation on the whole neighborhood of this pruned Julia set. That's the thing we were just discussing. And so you have this here, and they're quasi-conformally conjugates. And so I can take the Beltrami coefficient of this quasi-conformal map and take in the usual way the deformation of this Beltrami coefficient. And then what you can do is you can say, well, I'm going to try to find a map H lambda that has precisely this Beltrami coefficient. So what this Beltrami coefficient really says is, well, I assign at some point in Z, I'm looking at now a little disk in the range and look at what the preimage of this roughly looks like. Now, the map H is not actually always everywhere differentiable, but it's almost everywhere differentiable. And so it means that not complex differentiable, real differentiable. So the inverse of a small disk in a tangent space is an ellipse. And the point is that the quasi-conformal tells you that the dilatation, the eccentricity of this ellipse is bounded from above. And so what you're doing is you're kind of deforming this ellipse to make it more and more round. So you kind of take this family, well, if lambda at least is real, then you make it more round. And you kind of, your measurable Riemann mapping theorem, it tells you that actually, if you do that, there's also a corresponding map H lambda. And from the whole setup, this means that this map, a priori, this is just a topological map or quasi-conformal. But actually, from the way it's defined, this turns out to be an analytic map. And that's the beauty of it. And then actually, you get automatically a path-connected path between them. And if U was not actually a neighborhood of the interval, then in fact, this would not be clear at all. And we really need to have that U is a neighborhood of the interval, and this necklace neighborhood we discussed earlier would not suffice. So let me stop here. Thank you very much.
Good talk.
You have questions?
I do. Can I ask one?
Go on.
So where did the PL come into the story here? Can you say what PL is?
This is pruned polynomial-like. This is just an abbreviation that I stuck in here. So this is nothing other than this, this class of objects. I should have really defined it here.
I thought it was piecewise linear.
No. Sorry about that. No, that's definitely not what I meant. Thank you very much for asking.
More questions?
So the path connectedness is then the path lambda, right? As you increase lambda from 0 to 1, you get the path.
If you take lambda real, then in fact this map also will end up real. If you took lambda not real, then in fact you would have a non-real deformation of your map. But if lambda is real, then this actually connects F0 and F1.
Okay.
So Avila-Lyubich proved that the hybrid class is contractible actually, right? So the homologies are trivial. Can you prove this in this setting?
I thought about this a little bit, but at this moment, there's several things that I want to do first. So I haven't really thought much about it, but I think it's a really good question. And I'm not, at this moment, I'm not, I don't want to say yes or no. My feeling is that the answer might well be yes, but there's a few other things we really desperately need to do first. Thank you.
Sebastian, is there some relation between the polynomials and how they approximate? If you have one of these real analytic things that's transcendental or something like that, then when you take and truncate to a large degree, is there a relationship between such polynomial conjugacies and the big one, or are the transcendentals really very different?
Well, no, actually near the real line, near this interval, dynamical interval I, they would really be very, very similar. So suppose you took a quadratic map and a transcendental map, or even just a real analytic map that is defined on some kind of unspecified neighborhood of your interval. Then in fact, what the story is that these pruned, if I would prune the Julia set for this quadratic map, I would end up with a topologically similar, well, actually homeomorphic object for both objects, for the map, quadratic map F, and the real analytic map. So, and then in fact, it turns out they're even quasi-conformally the same. So that's really the point, that I want to sort of have a structure that even survives if you don't have this global domain.
Thank you.
Does that answer your question? I think it was Sheldon, isn't it? I don't see on my screen who it is.
That's right.
But I'm just guessing.
I think so. It's, well, the first question, which I thought was in your original one, when they're conjugate, you have this connected space. I presume that you don't have polynomials always in that space. In other words, they're really different in some ways when you go to the.
You're absolutely right. In fact, I think often they cannot be. But for example, if you took a real quadratic map, then if you take the conjugacy class, the only real quadratic map in this conjugacy class would be that particular quadratic map. It would be a unique point in there. So you immediately go outside the space of polynomials.
Thank you.
Some more questions? No. So let's thank Sebastian again. And we have a break.
Felix, just a moment, please. Now, I had the idea right now.